Hello. Today I'm going to be talking about the birthday problem, sometimes called the birthday paradox. And this is how it goes. So let's suppose you have a room, and unrelated people start entering the room, and you ask them to start comparing their birthdays. Now you imagine that most of the time, when two people compare, there's a very small chance of them matching the birthdays. So most of the time, they're not going to match. But if you get a large number of people in the room, you imagine there probably is a chance that eventually you'll find two that match. So here's the question. How many people do you need in a room before you have a 50-50 chance, a 50% chance of two people sharing a birthday? So maybe you think it's about 50. But then again, 50 only represents less than 1/7 of the possible number of birthdays. So maybe you want a few more than that. What about 100? But even with 100, there's still more than 2/3 of the possible birthdays left. So maybe you want half the number of possible birthdays. So there's 366 possible birthdays, if you include February the 29th. So we want 183 people maybe? Or maybe you think even more than that. Maybe 300. So I'll give you a couple of seconds to think about how many you need in the room, and then I'll tell you what the answer is. Okay, so here is the answer. The number of people you need in a room before you've got a 50-50 chance of two of them having the same birthday is 23. Yeah, just 23. So it's quite a counterintuitive result if you've never seen this before. Just how few people you need, but before you say I'm just telling lies and it's all wrong, we're going to prove it using probability. Okay, so when we're doing this proof, we're going to make some assumptions. The first is that February the 29th doesn't exist. Now, obviously it does exist, but it makes the math a little bit harder. So it doesn't really change the result very much, so we're going to ignore it for the moment. Second, we're going to assume that each birthday is equally likely to come up. So we're going to ignore like slight increases in certain days and whatever else. And lastly, we're going to assume that each of the people in that room are independent from each other. So we're not talking about a convention for twins or anything like that. So the importance of the independent condition is that we can start multiplying events together. Right, so to prove this, we usually phrase the opposite question. So instead of how many people before two people share the same birthday, what's the probability that no one shares a birthday? i.e. that every single birthday in that room is unique. So obviously when one person enters a room, you can't have a match because there isn't enough people yet. When the second person enters the room, to not match, it must avoid the birthday of the first person who's already in the room. So the 364 possible birthdays, it'll do that. So the chance is 364 in 365. So when the third person enters the room, they must avoid two birthdays. So now there's only 363 days left. So the chance of the third person avoiding both birthdays is 363 in 365. And then, to get the probability that none of them share a birthday, we multiply it by the result we had from the previous stage. So when the fourth person enters the room, it's 362 in 365 times what we had before. When the fifth person enters the room, we're trying to avoid 4 birthdays now, so it's 361 in 365 times what we had before, and each successive time we need to avoid 1 more birthday. By the time we have 9 people in the room,
the probability that everyone avoids each other's birthdays has dropped to about 90%. This means that the opposite condition, the chance that at least one pair shares a birthday, has nearly risen to 10%. By the time we have 15 people in the room together, the probability that everyone avoids each other's birthdays has dropped to less than 75%. This means there's a greater than 25% chance, 1 in 4, that the two of them will share a birthday, with only 15 people in the room. And as the 23rd person enters the room, the probability has now dropped to 49.27%. So that means the chance of two people having a birthday together is now above 50%.
So yes, this really means that you only need 23 people to be in a room together before there's a 50% chance that two of them have the same birthday. So next time you're in a room with a group of people, why not try and find out if two of those people have the same birthday? And in fact, it works in all sorts of situations. So in fact, by the time this video has had its 23rd view, there's a 50-50 chance that two of those viewers have the same birthday. And actually it ramps up really quickly. By the time this video has had 57 views, there's a 99% chance that two of them somewhere will have the same birthday. If it gets 100 views, there's a 1 in 3 million chance that no one shares a birthday. So a really tiny chance. So, thanks for watching.